Advance in image fusion techniques. During the past 2 decades, several fusion techniques have been proposed. Most of these techniques are based on the compromise between the desired spatial enhancement and the spectral consistency. Among the hundreds of variations of image fusion techniques, the widely used methods include, but are not limited to, intensity hue saturation, IHS, high-pass filtering, principal component analysis, PCA, different arithmetic combination, for example Brovy transform, multi-resolution analysis-based methods, for example pyramid algorithm, wavelet transform, and artificial neural networks, ANNs, etc. The lecture will provide a general introduction to those selected methods with emphases on new advances in the remote sensing field. In general, all above-mentioned approaches can be divided into 4 different types: signal level, pixel level, feature level, and decision level image fusion. Signal level fusion. In signal-based fusion, signals from different sensors are combined to create a new signal with a better signal-to-noise ratio than the original signals. Pixel level fusion. Pixel-based fusion is performed on a pixel-by-pixel basis. It generates a fused image in which information associated with each pixel is determined from a set of pixels in source images to improve the performance of image processing tasks such as segmentation. Feature level fusion. Feature-based fusion at feature level requires an extraction of objects recognized in the various data sources. It requires the extraction of salient features which are depending on their environment, such as pixel intensities, edges or textures. These similar features from input images are fused. Decision level fusion consists of merging information at a higher level of abstraction, combines the results from multiple algorithms to yield a final fused decision. Input images are processed individually for information extraction. The obtained information is then combined applying decision rules to reinforce common interpretation. The PCA transform converts intercorrelated multispectral, MS, bands into a new set of uncorrelated components. To do this approach, first we must get the principal components of the MS image bands. After that, the first principal component, which contains the most information of the image, is substituted by the panchromatic image. Finally, the inverse principal component transform is done to get the new RGB, red, green, and blue, bands of multispectral image from the principal components. The IHS fusion converts a color MS image from the RGB space into the IHS color space. Because the intensity, I, band resembles a panchromatic, PAN, image, it is replaced by a high-resolution PAN image in the fusion. A reverse IHS transform is then performed on the PAN together with the hue, H, and saturation, S, bands, resulting in an IHS fused image. Different arithmetic combinations have been developed for image fusion. The Brovy transform, synthetic variable ratio, SVR, and ratio enhancement, RE, techniques are some successful examples. The basic procedure of the Brovy transform first multiplies each MS band by the high-resolution PAN band, and then divides each product by the sum of the MS bands. The SVR and RE techniques are similar, but involve more sophisticated calculations for the MS sum for better fusion quality. Convenient fusion algorithms mentioned above have been widely used for relatively simple and time-efficient fusion schemes. However, several problems must be considered before their application. 1. These fusion algorithms generate a fused image from a set of pixels in the various sources. These pixel-level fusion methods are very sensitive to registration accuracy, so that co-registration of input images at subpixel level is required. 2. One of the main limitations of his and Brovy transform is that the number of input multiple spectral bands should be equal or less than 3 at a time. 3. These image fusion methods are often successful at improves the spatial resolution, however, they tend to distort the original spectral signatures to some extent. More recently, new techniques such as the wavelet transform seem to reduce the color distortion problem and to keep the statistical parameters invariable. Multi-resolution or multi-scale methods, such as pyramid transformation, have been adopted for data fusion since the early 1980s. The pyramid-based image fusion methods, including Laplacian pyramid transform, were all developed from Gaussian pyramid transform, have been modified and widely used. In 1989, Mallet put all the methods of wavelet construction into the framework of functional analysis and described the fast wavelet transform algorithm and general method of constructing wavelet orthonormal basis. On the basis, wavelet transform can be really applied to image decomposition and reconstruction. Wavelet transforms provide a framework in which an image is decomposed, with each level corresponding to a coarser resolution band. For example, in the case of fusing an MS image with a high-resolution PAN image with wavelet fusion, the PAN image is first decomposed into a set of low-resolution PAN images with corresponding wavelet coefficients, spatial details, for each level. Individual bands of the MS image then replace the low-resolution PAN at the resolution level of the original MS image. The high-resolution spatial detail is injected into each MS band by performing a reverse wavelet transform on each MS band together with the corresponding wavelet coefficients. Generic flowchart of wavelet-based image fusion. In the wavelet-based fusion schemes, detail information is extracted from the PAN image using wavelet transforms and injected into the MS image. Distortion of the spectral information is minimized compared to the standard methods. In order to achieve optimum fusion results, various wavelet-based fusion schemes have been tested by many researchers. Among these schemes, several new concepts/algorithms were presented and discussed. Kahn provided a method for fusing SAR and visible MS images using the curvelet transformation. The method was proven to be more efficient for detecting edge information and denoising than wavelet transformation. Curvelet-based image fusion has been used to merge a Landsat ETM plus panchromatic and multiple spectral image. The proposed method simultaneously provides richer information in the spatial and spectral domains. Donahoe et al. Presented a flexible multi-resolution, local, and directional image expansion using contour segments, the controllet transform, to solve the problem that wavelet transform could not efficiently represent the singularity of linear/curve in image processing. Controllet transform provides flexible number of directions and captures the intrinsic geometrical structure of images. In general, as a typical feature-level fusion method, wavelet-based fusion could evidently perform better than convenient methods in terms of minimizing color distortion and denoising effects. It has been one of the most popular fusion methods in remote sensing in recent years, and has been standard module in many commercial image processing softwares, such as ENVI, PCI, ERDOS. Problems and limitations associated with them include, 1. Its computational complexity compared to the standard methods. 2. Spectral content of small objects often lost in the fused images. 3. It often requires the user to determine appropriate values for certain parameters, such as thresholds. The development of more sophisticated wavelet-based fusion algorithm, such as ridgelet, curvelet, and controllet transformation, could improve the performance results, but these new schemes may cause greater complexity in the computation and setting of parameters. Artificial neural networks, ANNs, have proven to be a more powerful and self-adaptive method of pattern recognition as compared to traditional linear and simple nonlinear analyses. The ANN-based method employs a nonlinear response function that iterates many times in a special network structure in order to learn the complex functional relationship between input and output training data. The general schematic diagram of the ANN-based image fusion method can be seen in General schematic diagram of the ANN-based image fusion method. The input layer has several neurons, which represent the feature factors extracted and normalized from image A and image B. The function of each neuron is a sigmoid function given by N. The hidden layer has several neurons and the output layer has one neuron, or more neuron. The ith neuron of the input layer connects with the JTH neuron of the hidden layer by weight phi, and weight between the JTH neuron of the hidden layer and the TTH neuron of output layer is VJT, in this case t equals 1. The weighting function is used to simulate and recognize the response relationship between features of fused image and corresponding feature from original images, image A and image B. The ANN model is given as follows. In equation 6, y equals pixel value of fused image exported from the neural network model, q equals number of nodes hidden, q8 here, vj equals weight between JTH hidden node and output node. In this case, there is only one output node, c equals threshold of the output node, hj equals exported values from the JTH hidden node. Where vi equals weight between ith input node and the JTH hidden node, I equals values of the ith input factor, n equals number of nodes of input, n5 here, hj equals threshold of the JTH hidden node.